Welcome to The Quantum of Insight, the podcast where we explore ideas at the intersection of science, technology, and philosophy. Today, we have a very special guest, Jean-Louis, whose latest research, AI tokens as quanta of information versus quanta in quantum physics, is making waves on ResearchGate. Jean-Louis, welcome to the show.
Thank you. It's great to be here. I do not think my paper is making waves, but thanks for helping me to promote it with this podcast.
Let's dive right in. Jean-Louis, could you tell us what motivated you to write this paper? What was the objective behind comparing quantum physics concepts with elements of artificial intelligence, particularly in the context of language models?
Certainly. The inspiration came from noticing that terms like quantum, uncertainty, and collapse are often used, sometimes metaphorically, to describe processes in AI and information theory. I wanted to dissect these analogies to see how far they really hold up. My aim was to demonstrate that while the comparison is evocative, it tends to be superficial. By breaking down the definitions and underlying principles of these concepts in both quantum physics and AI, we can appreciate the true nature of each without conflating the two.
That sounds like a fascinating endeavor. Let's start with the basics. In your paper, you discuss the idea of discreteness and dimensionality. Can you explain how tokens in large language models or natural language processing are analogous to quanta in physics, and what the key differences are?
Absolutely. In large language models or natural language processing, tokens are the basic indivisible units of text. They're analogous to physical quanta in that they represent the smallest building blocks, in this case, elements of language. However, unlike physical quanta that come with specific units like Newton meter seconds, tokens are abstract and unitless. They're numbers in a vector space without any physical dimension. This distinction is crucial because it highlights that while both are fundamental in their respective fields, tokens and physical quanta operate on entirely different scales and principles.
That makes sense. Now, another interesting point you raised is the language dependency of tokens versus the universality of physical quanta. Could you elaborate on that contrast?
Sure. Tokens are inherently tied to the natural language from which they are derived. For example, the tokens produced when processing English text capture specific linguistic nuances, idioms, and syntactic rules. In contrast, if you process text in another language, say Dutch or Mandarin, the tokens will differ accordingly. On the other hand, physical quanta, such as Planck's constant, are universal. Their values and units remain invariant, regardless of the context or language. This contrast shows how tokens are culturally and linguistically embedded, while physical constants in mathematical or physical equations and the equations themselves are universally applicable.
That's a fascinating distinction. Moving on, your paper also delves into the differences between governing equations in physics and the learned associations in AI. What did you find in comparing these two?
In physical equations, especially in fields like electromagnetism and quantum mechanics, differential operators like gradients, curls, and divergences play a central role. They are part of governing equations, such as Maxwell's equations and Schrödinger's equation, which describe how physical systems evolve under well-defined conservation laws and symmetries. In contrast, the associations between vector embeddings in NLP are not determined by such strict laws. Instead, these embeddings result from statistical learning. They are formed by optimizing over vast amounts of data, capturing empirical relationships without any explicit differential operators. This means that while physical systems are governed by immutable laws, the relationships in an embedding space are emergent and data-dependent.
That really underscores the fundamental differences between the two domains. Finally, your paper addresses the notion of uncertainty, both in quantum physics and in AI response generation. Can you walk us through how these concepts compare and what insights you discovered?
Certainly. In quantum mechanics, uncertainty is a fundamental property. The wave function of a system represents a superposition of all possible states, and only upon measurement does it collapse into a specific state, following precise probabilistic rules like the Born rule. This uncertainty is intrinsic but mathematically well defined in AI, particularly with language models. There's also uncertainty, but it manifests differently. When a model generates text, it essentially evaluates a probability distribution over potential continuations and selects the one that best fits the context. Although this process may seem opaque or black box to the user, it is driven by deterministic algorithms applied to a learned statistical distribution. In both cases, what might appear as randomness is actually underpinned by statistical determinism, though the origins and mechanisms are entirely different.
That's a clear and nuanced explanation. To wrap up our conversation, how do you synthesize these ideas? What is the main takeaway from your paper?
The main takeaway is that while the metaphors linking quantum physics to AI, especially when discussing tokens and uncertainty, are engaging and thought-provoking, but that they can also be misleading if taken too literally. Tokens in NLP, despite their superficial similarity to physical quanta, operate in a completely different realm. They're abstract, unitless, and tied to language, whereas physical quanta are governed by immutable, universal laws. By dissecting these concepts, we can better appreciate the distinct principles underlying each domain and avoid conflating how statistical inference in AI actually works. The underlying me cannot be compared with the fundamental behavior of physical systems.
Jean-Louis, thank you for this insightful discussion. Your work not only challenges superficial comparisons, but also deepens our understanding of both AI and quantum physics. It's been a pleasure having you on the show.
Thank you for having me. It's been a great conversation, and I appreciate the opportunity to share my research.
And thank you to our listeners for tuning in to The Quantum of Insight. Don't forget to check out Jean-Louis' paper on ResearchGate. Until next time, keep questioning and exploring the boundaries of knowledge.